Hi everyone, welcome to the 23rd session on ECT 204 Signals and Systems. Today we will attempt to compute Fourier transforms based on the properties. The properties you have seen in the last video. So based on those properties we will derive some Fourier transform, especially those of singular signals, periodic signals, etc. This video is organized into your learning outcomes, then computation of Fourier transform with linearity and time shift. Here we will compute the Fourier transform of a bipolar signal, bipolar rectangular signal. Then we will compute the transform with the convolution theorem. Here we will compute the the transform of a triangular signal. A triangular signal is represented as the convolution of two rectangular pulses. Then convolution theorem is applied to compute the Fourier transform. Then transforms of singular signals like SG&T, etc. Then how to compute the Fourier transform of certain periodic signals. Then Fourier transform of periodic impulse train. This will be very useful when you reconsider sampling. What will happen to the spectrum of the signal on sampling? There the Fourier transform of a periodic impulse will be of great use to you. Then finally an interesting thing is Gaussian pulse. What is a Fourier transform of a Gaussian pulse? Then the summary of understanding. So your learning outcomes are you will compute the Fourier transform based on properties. Then you will compute the Fourier transforms of singular signals like UT, the SG and T, etc. Then you will learn to compute the Fourier transform of periodic signals. Then you will compute the Fourier transform of periodic impulse train. This will be very useful to you later when you reconsider the sampling of signals. Then in the end you will compute the Fourier transform of Gaussian pulse. Now let us compute the transform with the linearity property and time shift property. In the last classes we have seen the Fourier transform of a short pulse, a rectangular pulse of width t. Now let us look at this signal, this bipolar signal, this bipolar rectangular signal. This is from minus t to 0 it is minus a, and from 0 to t it is a. Everywhere else is a 0. Now you can consider this as a delayed, this part as an advanced version of my rectangular pulse. That is, the rectangular pulse is advanced by t by 2 units. This is a rectangular pulse that is delayed by t by 2 units. Earlier the rectangular pulse we saw was from minus t by 2 t by 2. Now this is shifted to the right by t by 2. This is a rectangular pulse negated and shifted in the negative time direction, that is advanced in time by t by 2 units. So we know that, so we can consider the whole signal xt as a summation of this part, this pulse from 0 to t, and this pulse from minus t to 0. So we know that a pulse of height a, that is centered at t equal to 0, and a total width of t has a Fourier transform of at sinc ft. Now, what is a Fourier transform? This xt can be written as a combination like this, like a p t minus t by 2 by t. That means it's a pulse of height a and width t, but that is delayed by t by 2 units. That is, originally it was at originally the center was at 0, but it is shifted by t by 2 units. Then minus ap pulse t plus t by 2 divided by t, that is a pulse of width t but advanced in time by t by 2. Now by using the linearity and time shift property, the Fourier transform of this xt will be at sinc ft, that is multiplied by e raised to minus j 2 pi ft, because it is delayed by t by 2 units. So it is e raised to minus j 2 pi f t by 2, so it becomes e raised to minus j pi ft, minus at sinc e raised to j plus j pi ft. It is actually j pi 2 pi f t by 2. It becomes e raised to j pi ft. Now what happens is this is e raised to j theta minus e raised to minus j theta. That is a 2j sine theta. So it's there is a negation here. It is e raised to minus j theta minus e raised to minus e raised to j theta. So it is a minus 2j sine theta. So it becomes at sinh ft multiplied by minus 2j sine pi ft. So the resulting transform will be minus 2j at sinh ft sine pi ft. If I take the modulus value of this, you can see that this is a variation. Figure 1 shows a variation of the absolute value of the above transform. We can demonstrate with Python. So this is a spectrum of or the Fourier transform of a bipolar pulse. Here frequency I took from minus 100 to 100 with an increment of 0.1, and capital T I took as 0.05 second, and the amplitude as 1. So this is a function x is 280 sinh ft multiplied by sine pi ft, and the absolute value is plotted against f. So here if I run, this is bipole. Now you can see the spectrum or the Fourier transform like this. Since there is a multiplication by sine pi ft, which is 0 at t equal to 0, now what happens is you can see that xf is 0 at t equal to 0. Okay, so that means the DC component in it is 0. You can see that the signal has got equal positive and negative excursion. That is very easy to say by observing the signal, but the spectrum or the Fourier transform confirms this fact that at f equal to 0 the spectrum is 0. There is no DC part in this. So this particular pulse is good for communication through telephonic communication through transformers, coils, etc. Landline telephony, the digital telephony. There is one pulse that is used in digital telephony, bipolar pulse. So you can see that there is a 0 at f equal to 0, and you can see that my sing pulse that is modulated by the sine function. So this is how the Fourier transform varies. Let us go back to the presentation. So the presence of that sine function, sine pi ft, inserts a 0 at f equal to 0. Now let us compute the transform of a triangular signal with the convolution theorem. In the previous sessions we saw that a convolution in the time domain that appears as a multiplication in the frequency domain. So let us use this convolution theorem to compute the Fourier transform of this triangular signal. This triangular signal is 0 outside the interval minus t by 2 to t by 2. Inside the interval it is a linear function like this. From minus t by 2 to 0 it is increasing, and from 0 to t by 2 it is decreasing. Now this signal xt can be either you can perform the usual integration and all that, or else you can use a convolution theorem to get the transform very quickly. So here I use a convolution theorem. Here you can see that this is a convolution between two pulses, okay, two rectangular pulses centered at 0 and width t by t and height root a. So you can see that if such a pulse is convolved with itself, you get this triangular signal. If this root a, that is a pulse of height root a or amplitude root a spanning from minus t by 2 to t by 2 centered at origin, if this is convolved with itself, you get this triangular signal. Okay. So xt can be written as a convolution between root a p t by t convolved with root a p t by t. What is this p t by t? That's a pulse of width t centered at origin. So equal excursion to negative and positive time axis to t with t by 2 excursion. So we know that from our earlier discussion, we know that pt by t has a Fourier transform of t sinh ft, or pt by t has a transform at sinh ft. So here the amplitude is only root a. So the Fourier transform of this pulse is this particular pulse is root a t into sinh ft, root a t into sinh ft. Now since xt is a convolution between two pulses, xf will be the multiplication between their Fourier transforms. So what is this? Xf will be Fourier transform, this Fourier transform square. So it becomes at square sin square ft. So the Fourier transform of my triangular signal is at square sin square ft. So what I can do is, I will you can see this demo. Here it is. How this varies is, it is at square sin ft times sin ft with t as 0.05 and a as 1. So if we run this, you can observe the variation of the absolute value of Fourier transform. Here you can, this at square sin square ft function. Okay, you can see that the DC value is very prominent. Okay, because there's a strong DC component in the signal, so DC value is prominent. But side lobes are minimized. The side lobes are now subdued. Okay, because of the squaring operation, the side lobes are somewhat subdued, but main lobe is now very prominent. DC component is very strong. You can run this code and appreciate it at home. Then let us compute the transforms of some singular signals. Say Fourier transform of xt equal to delta t. Delta t is 1 for t equal to 0, 0 elsewhere. It's a Kronecker delta function. So xf will be minus infinity to infinity xt raised to minus j 2 pi ft. Well, the Fourier transform of the delta function is xf is minus infinity to infinity xt raised to minus j 2 pi ft. So this function is 0 everywhere except t equal to 0. At t equal to 0, the value is 1. So it is 1 e raised to 0 dt. Only at t equal to 0. So what happens is, this is 1. xf is only exists for only at xt exists only at t equal to 0. It is at t equal to 0, xt value of xt is 1, and e raised to minus j 2 pi of 0, that's a 1. So this integral simply vanishes. There's only one value that at t equal to 0, so it is xf is 1. So you can see that xf is constantly 1 from minus infinity to infinity. It is observed that the energy in the transform is equally distributed over all frequencies from minus infinity to infinity, while the energy in the time domain, that is concentrated to t equal to 0. You can see that in the time domain, the whole of the energy of xt is concentrated to t equal to the interval t equal to 0. It's an extremely localized function. Now, in the what happens in the frequency domain, all the energy is equally distributed. Its spectral value is 1 throughout. It is distributed from minus infinity to plus infinity. Okay, this xf is spectrally white because all frequencies are available in xf with equal participation. So xf is a spectrally white signal. Now let us use the derivative property to compute the Fourier transform of SGNT, the sine function, and ut. Now let xt equal to SGNT. What is the shape of SGNT? It is minus 1 for t less than 0 and 1 for t greater than 0. So what I can do is, I cannot easily take this function. I cannot compute the xf of this function because there is a discontinuity here. So what I can do is, I can differentiate this signal, so that if I take the derivative of signal from minus infinity to 0, it will be 0, and from 0 to infinity it will be 0, because both here we see a constant, here we see a constant. So derivative exists only at t equal to 0. What is the derivative? It is a vertical edge here. What is the change? That is, it is changing from minus 1 to 1. So you get an impulse of height 2 here. Okay, the derivative. Everywhere else the derivative will be 0. From minus infinity to 0, it's a minus 1, derivative is 0. From 0 to infinity, the value is a 1, the derivative is 0. Where does the derivative exist? Only at t equal to 0. What is it? It's a delta function. What is the size of the delta function? The change is from minus 1 to 1. So it is the value is 1 minus minus 1, that is 2. So it is 2 delta t. dxt by dt is 2 delta t. Now we can take the derivative. Now even though I cannot take the Fourier transform of this one, I can take the Fourier transform of this one now. Now what is the Fourier transform of a derivative? It is j 2 pi f into xf. That is, what is the derivative of delta t? It is a 1. So it becomes a 2. J 2 pi f xf is 2. So what is the xf? That will be 1 by j pi f. 1 by j pi f. This is the value of your Fourier transform. What is xf? That is 1 by j to pi f. Okay. Now you can compute the Fourier transform of the unit step also. What is a unit? How is a unit step related with my SGNT? It is 2 SGNT. If I multiply this by 2, it will become 2 here and minus 2 here, and I can add a Now, how is ut related with my SGNT? Ut will be 1 plus SGNT by 2. That is, if I add 1 to this function, it will be, this function will be have a value of 2 from 0 to infinity. Minus infinity to 0, if I add 1 to this, from minus infinity to 0, the value will be a 0. Here the value will be 2. When I divide by 2, it becomes a 1, it becomes a unit step. So ut is SGNT plus 1 all divided by 2. So now we know the Fourier transform of SGNT, we should know the Fourier transform of 1. So by duality, you know that delta t has a Fourier transform of 1. So by duality theorem, 1 has a Fourier transform of delta f. This is a duality theorem. That is, delta t has a Fourier transform of f. So by duality theorem, 1 has a Fourier transform of delta f. So the Fourier transform of ut will be uff, that will be 1 by j pi f, because that is the Fourier transform of SGNT, plus delta f. This is a Fourier transform of 1 divided by 2. So it becomes 1 by j 2 pi f plus half of delta f. 1 by, so the Fourier transform of ut, the unit step will be 1 by j 2 pi f plus half of delta f. So this is this 1 by 2 pi f is a kind of a rectangular hyperbola. Xf is equal to 1 by 2 pi f is a rectangular hyperbola that is superimposed with a delta function, a canonical delta function with amplitude half. So we will appreciate it with a Python demo. Here actually I have computed 1 by 2 pi f and overlapped it with an impulse signal. Okay. So here I have written an impulse signal as this, return append zeros m, append 1. So a 1 is preceded and succeeded by some zeros to make an impulse signal. Then I make a frequency vector from minus 20 to 20. Then I have computed x equal to 1 by 2 pi f. Okay. And I have put this this impulse signal over that. Okay, you can run UTFT. Here you can see how this varies. This 1 by 2 pi f, this is a rectangular hyperbola. This is an absolute value. That's why it is appearing in the positive side. So this is actually 1 by 2 pi f. This is actually mode 1 by 2 pi f. This is another mode 1 by 2 pi f. And this is an impulse of height 0.5. This is an impulse of height 0.5. These two curves, they depict the 1 by 2 pi f part, and this impulse represents my impulsive part, half delta f. So let me go back to my presentation. Now, some cases you can compute the Fourier transform of a periodic signal. Though Fourier transform primarily is used for non-periodic signals, it can be applied to periodic signals xt equal to xt plus t by combining with the Fourier series. So the periodic signal is expressed as a Fourier series as xt equal to k from minus infinity to infinity ck e raised to j 2 pi kt by t, or this is actually minus infinity to infinity ck into 1 e raised to j 2 pi kt by t. If I take Fourier transform on both sides, x of t Fourier transform will be x of that this is k from minus infinity to infinity ck. Now you can see that this is 1 e raised to j 2 pi kt. 1 has a Fourier transform of delta f. So that is multiplied by e raised to j 2 pi k. So this is delayed by k by t units. It is a j 2 pi k by t. So this delta f is delayed by k by t units. So this occurs for every k from minus infinity to infinity. So it looks like an infinite sum of impulses of height ck placed at around every 1 by t. Now, the important thing is we can compute the Fourier transform of a periodic impulse train with this result. So this is very useful when you consider the sampling of signals. What happens to when you try to analyze what happens to the spectrum of the signal on sampling? This theorem will be very useful to you. So let us consider an impulse train xt equal to k from minus infinity to infinity delta t minus kt. Okay, so these are impulses placed like this every t second apart. Okay. Here you can see these impulses placed at every kt from k from minus infinity to infinity. So this is how the impulse train looks like. Now let us compute the Fourier transform of this signal. So xt will be, so you have to compute the Fourier coefficient first of all. That is ck will be 1 by t from 0 to t delta t raised to minus j 2 pi kt by t dt. So this here you can compute the Fourier coefficient ck as 1 by t from 0 to t delta t e raised to minus j 2 pi kt by t. So delta t has value only at t equal to 0. So this whole integral defaults to 1. So ck is 1 by t. Okay. So what is a Fourier transform? By earlier theorem, we know that x of is sigma k from minus infinity to infinity ck delta f minus k by t. So this becomes x of f, that becomes k from minus infinity to infinity 1 by t. This is my ck delta f minus k by t, or it is 1 by t k from minus infinity to infinity delta f minus k by t. Now you can see that the Fourier transform of that impulse train is another impulse train in the frequency domain, each with a height of 1 by t spaced 1 by t apart in the frequency domain. So here you can see that in the frequency domain you get another impulse train, but spaced at every 1 by t, 2 by 1 by 2t, etc. What this result says is that the Fourier transform of an impulse train is an impulse train in the frequency domain with a height 1 by t spaced at every 1 by t. So that looks like this. This is delta f f minus k by t times 1 by t. So this has a height of 1 by t, and here you can see that in the frequency domain this impulse train looks like this. The impulses occur at every 1 by t, every k by t, that is 1 by t, 2 by t, 3 by t, minus 1 by t, minus 2 by t, etc. And the height of every impulse is 1 by t. So the impulse train in the time domain with the period t appears as another impulse train in the frequency domain with height 1 by t and spaced 1 by t hertz apart. So the Fourier transform of a Gaussian pulse is very interesting because You know that in all other cases, say for example, if I take the Fourier transform of a rectangular signal, you get a sinc pulse. If you take the Fourier transform of a triangular signal, you get another shape, say a sinc square function. But the Fourier transform of a Gaussian pulse is very interesting. When you take the Fourier transform of a Gaussian pulse, you get another Gaussian pulse. That's a specialty of Gaussian signal. So let us consider the Gaussian signal xt equal to e raised to minus at square with a greater than 0 for positive a. And xf will be minus infinity to infinity e raised to minus at square into e raised to minus j 2 pi ft dt. Now you cannot simply compute this integral. It is wise you take a derivative like dxf by df I take. Okay, dxf by df I take, so that it becomes minus infinity to infinity minus j 2 pi t e raised to minus at square, that will remain there. Derivative of e raised to minus j 2 pi ft will be e raised to minus j 2 pi ft multiplied by minus j 2 pi t dt. So I can take out this minus 2 pi j outside, and this becomes minus infinity to infinity t e raised to minus at square e raised to minus j 2 pi ft dt. Now this integration can be done by parts, that is minus j 2 pi into, I take this e raised to minus j 2 pi ft as a first function, so it is first function into integral of the second, that is integral of t e raised to minus at square. So I take e raised to minus j 2 pi ft as the first function and t e raised to minus at square as a second function. So it is from minus infinity to infinity t e raised to minus at square dt minus integral of derivative of the first. Derivative of this thing will be minus j 2 pi f e raised to minus j 2 pi ft. Derivative of this first function, that is minus j 2 pi f e raised to minus j 2 pi ft. Then derivative of the first into integral of the second. Integral of the second is minus infinity to infinity t e raised to minus at square dt. Now, so dxf by df, this will be that is minus j 2 pi into, this part will be, this is t e raised to minus at square dt. So integral of this one. So what is that? That is a e raised to minus 1 by 2a e raised to minus j 2 pi ft e raised to minus at square from minus infinity to infinity. Okay. So plus I have a j 2 pi I have a 2 positive sign here, so it becomes a plus j 2 pi into minus infinity to infinity. This will be minus j 2 pi minus j 2 pi f e raised to minus j 2 pi ft into minus 1 by 2a e raised to minus at square. If I take the derivative of this one, it will be e raised to minus at square. Okay. So for the first part of this summation, this will be 0, because when I put the upper limit minus plus infinity here, it will be e raised to minus infinity, it will be 0. If I apply the lower limit, what happens is this will be positive, but this e raised to minus at square term will be 0. So this the first part, this part simply vanishes. Okay, this part simply vanishes. Only the this integral remains. So what happens to that integral? It will be that will be 0 plus j 2 pi into minus infinity to infinity minus j 2 pi f e raised to minus j 2 pi ft into minus 1 by 2a e raised to minus at square dt. Now I can take out this f term here. So if I take it out, it will be, I have a j here, that will be a minus 1. Then I have another minus 1 here, so total will be a negative value. It will be minus 4 pi square f by 2a. Okay, I can take out this integral, minus infinity to infinity e raised to minus j 2 pi ft e raised to minus at square dt. Now what is this? This is my self-same xf. We know this is my xf. Okay, this is my xf. So I have got minus 4 pi square f by 2a into xf. Now I have got a differential equation in xf. What this does is dxf by df is equal to minus 4 pi square f by 2a into xf. Now I can take this xf to this side and df to this side, so that this becomes a differential equation like this: dxf by dxf, that is equal to minus 4 pi square f by 2a into df. That is, I took this xf to this left side and df to the right side, so it becomes dxf by xf, that is minus 4 pi square f by 2a df. Now if I integrate this one, you can see that this of the form 1 by x dx form, that is what is the integral of this one? It will be log fx. Okay, this will be Nusselt logarithm of xf, that will be minus 4 pi square. What is the integral of f df? That will be f square by 2. Okay, integral of f df will be f square by 2. So it becomes 4 pi square f square by 4a plus some constant of integration, say c1. So this so I can write this xf, if I take exponentials on both sides, it will be xf will be e raised to minus 4 pi square f square by 4a plus c1. So that will be e raised to c1 times e raised to minus 4 pi square f square by 2a. So this e raised to c1 I can write at another constant, say c. So xf will be c e raised to minus 4 pi square f square by 4a. Now I have to find the constant of integration. So for finding the constant of integration, what I can do is I can apply some initial condition, like I can say put f equal to 0 in the first equation, that is here. In this equation, if I put f equal to 0, okay, that will be x of 0. So if I put f equal to 0 here, this kernel will disappear, it will become 1. So it will be minus infinity to infinity e raised to minus at square dt. X of 0, capital X of 0 will be minus infinity to infinity e raised to minus at square into 1 dt. So I can write here, so x of 0 will be minus infinity to infinity e raised to minus at square dt. That is equal to, what will happen at f equal to 0? When f equal to 0, x of 0 will be c times e raised to 0, that will be x of 0 will be c. So x of 0 is c. Now, you know, by Gaussian, you know the Gaussian PDF, integral of a Gaussian PDF should be 1, because it's a probability distribution. We all know the well-known result, 1 by root 2 pi sigma square minus infinity to infinity e raised to minus t square by 2 sigma square dt. This, what is this? This is a Gaussian PDF of variance sigma square and mean 0. This is equal to 1, because the sum of all probability or integral of all the PDF or all values should be 1. So here you can see that this should be integral from minus infinity to infinity e raised to minus at square. So you can see that here you can see that 2 sigma square is actually 1 by a. Okay, here you can see that this 2 sigma square, if I match these two equations, 2 sigma square is 1 by a. Okay, so x of 0 will be that will be this e raised to this integral from minus infinity to infinity e raised to minus t square by 2 sigma square will be 2 pi sigma square. So it will be root of a by 2 pi. Okay, root of a by 2 pi, that will be root of 2 pi sigma square into c. Okay, that means so x of 0 will be root of a by 2 pi, so it is the same as root 2 pi sigma square, or c becomes root of pi by a. So x of f will be root of pi by a e raised to minus 4 pi square f square, root of pi by a e raised to minus pi square f square by a. Now you can see that this Gaussian pulse in the frequency domain. This is a Gaussian pulse in the frequency domain. So we can use a Python demo to get these signals. This is a Gaussian pulse in the time domain, and this is a Gaussian pulse in the frequency domain. The second one is a Fourier transform of the first one. So let us compute that. I'm trying to realize a small x, these are psi pi and py lab are involved, and a frequency value and time value from minus 20 to 20 with an increment of 0.25 is taken. A is taken as 0.01, and small x is my exponential signal e raised to minus at square, and capital X is the Fourier transform, that is root of pi by a into exponential of minus pi square f square by a square. By a, not a square, e raised to minus pi square f square by a. Now on a subplot, on two subplots, I plot this small x and capital X. So we will run this code with the run goes. You can see that. You can see that this is a Gaussian pulse in the time domain. This is another Gaussian pulse in the frequency domain, but it's a much steeper one, much sharper one. I will zoom this. Yeah, it's a much sharper one, but it's also a Gaussian pulse. Oh, did I make any mistake? Yeah, 4 pi square f square. Okay, that is how the Fourier transform of a Gaussian pulse look like. Now coming to the summary of understanding. In this video, you compared the Fourier transform based on properties like the Fourier transform of a bipolar rectangular signal, Fourier transform of a triangular signal, etc. Then you compared the Fourier transform of singular signals like SGNT, UT, etc. Then you learn to compare the Fourier transform of periodic signals, okay, using Fourier series. Then you compare to the Fourier transform of periodic impulse train. That will be very useful when you reconsider sampling. Then you compare to the Fourier transform of a Gaussian pulse. And that is the end of this presentation. I thank you all.